Right now, your computer's operating system believes it is, well, basically in total control of your machine.
Oh, absolutely. It thinks it's the boss.
Right. It thinks it knows every process you're running, every file you are touching, and every argument you're passing through the command line. But what if your command line interface decided it simply didn't trust your operating system anymore?
Which is an incredibly wild concept to wrap your head around.
It really is. Like, what if your shell started actively lying to the underlying machine? Just straight up encrypting its own footprints and, operating on a mathematical level of autonomy that completely bypasses traditional security models.
It is a radical proposition, for sure. I mean,
Mhm.
we are so accustomed to the shell acting as just this simple, obedient messenger between you and the kernel.
Yeah, you type a command, the shell hands it over.
Exactly. You type a command, the shell hands it directly to the operating system in plain text. The operating system executes it and then hands the result back. That relationship has been the bedrock of Unix-like environments for, what, half a century?
At least. Probably more at this point.
Right. So to introduce a layer that actively obfuscates its behavior from the host environment, that fundamentally rewrites the entire hierarchy of trust on a local machine.
And that is exactly what we are exploring today. We are doing a deep dive into the architecture of a fascinating piece of source material, the documentation for a tool called Moonshine.
Moonshine.
It's a great name. It is. It stands for Monster on Shell in Engine. And right off the bat, it is described as an autonomic, high-fidelity shell replacement engineered specifically for the Gnosis monorepo. Okay, let's unpack this.
Let's hear it.
Because if you are managing a massive architecture, like a monorepo, you already know the pain points of traditional shells.
Oh, the pain is very real.
You're dealing with thousands of interconnected services, right? Front-end clients, back-end microservices, sprawling dependency trees, all living in one giant repository. And when you try to orchestrate automated workflows across that kind of scale using standard bash or Z scripts, the underlying physics of how those shells operate just it becomes a massive liability.
The liability really comes down to the fundamental execution model. I mean, traditional shells were designed for human typing commands, or at best, a simple linear sequence of automated steps.
Read line 1, execute line 1.
Exactly. They operate on this blocking sequential paradigm.
Yeah.
You execute line 1, the shell process waits for line 1 to return a success or failure code. Then, and only then, it moves to line 2.
Which is fine for basic stuff.
Sure, it's fine for basic stuff. But when you try to scale that linear, read it like a book execution model to a monorepo, where you might need to concurrently compile a Rust backend, transpile a massive TypeScript frontend, and spin up a suite of Dockerized databases.
All at the same time.
All at the same time, with complex, interdependent success states. The shell just becomes an enormous bottleneck. It simply wasn't built to orchestrate large-scale concurrent topologies.
Which is why Moonshine completely rips out that foundational execution model. I mean, it just throws away. It doesn't read scripts top to bottom at all. It treats your commands as a control flow graph.
A CFG, yeah.
Right, a CFG. Instead of a linear script, you are basically mapping out a highly complex web of operations. The engine parses the relationships and dependencies between your commands first.
It looks the whole picture.
Yeah, it figures out exactly what can happen simultaneously, and then it navigates that graph.
And this shift from linear scripting to topological graph execution, it requires a completely different vocabulary for how commands interact. Moonshine introduces a paradigm it calls FRF.
FRF. Fork, race, fold.
Fork, race, fold. Exactly.
Let's break down the mechanics of this because it's a brilliantly aggressive way to handle concurrency. You still have your standard sequential execution, obviously. You put a semicolon between two commands, and stage 2 waits for stage 1.
Standard stuff.
Standard stuff. But then you have the fork. You separate two commands with an ampersand, and the Moonshine engine explicitly branches the control flow graph.
Right, and we should clarify that. It doesn't just push a task to the background like a traditional shell.
No, not at all. It actively provisions parallel execution states within the engine's internal topology.
The distinction there is critical. Backgrounding a task in bash with an ampersand is often just a fire-and-forget operation. The shell spawns the process and largely relinquishes control. Right, making it incredibly difficult to manage standard output or error.
Exactly. Or handle complex exit codes asynchronously. By making the fork a native topological concept, Moonshine retains absolute high-fidelity control over both branched pathways. It knows exactly when both forks complete, fail, or hang.
Which allows it to merge or fold the data back together predictably,
Precisely. That's the fold in FRF.
which perfectly sets up the most aggressive command in the Moonshine arsenal, which is the race. You wrap two commands in brackets with the race keyword, and the rule is simple: first to finish wins, and the loser is actively canceled.
Actively and brutally canceled.
It's amazing. I was thinking of an analogy for this. It's like if you need a specific package, so you dispatch two different delivery drivers with the exact same package on two different routes.
Okay, I like this. And the absolute second driver A arrives and hands you the package. Driver B is instantly eradicated from existence to clear up traffic.
Eradicated from existence. I mean, what's fascinating here is the sheer brutality of that cancellation.
Yeah.
It doesn't just ignore the slower process's output, it terminates the process at the OS level.
And it just kills it.
It kills it. And in a monorepo context, this is a masterclass in aggressive resource conservation.
Yeah.
Let's say you need a specific dependency resolved to unlock the next 50 nodes in your control flow graph.
Right.
You might ping a local cache, a network cache, and a remote server, all simultaneously using a race. The instant the local cache returns the data, the network requests are killed. You aren't just saving time.
They're saving resources.
You are instantly freeing up network sockets, RAM, and CPU cycles that the rest of your graph desperately needs to continue its parallel execution.
Okay, hold on a second. I need to push back on this because active cancellation sounds incredibly dangerous if we think about state.
Oh, absolutely.
Let's say you are racing two compilation processes or, two commands that are writing temporary files to the disk. If you aggressively kill the loser mid-execution, what happens to the half-written data? Doesn't the race concept risk completely corrupting the state of your machine?
It risks leaving orphan zombie files everywhere, yeah. That is the exact right question to ask. And it highlights a forced paradigm shift for anyone developing within the Moonshine ecosystem.
Okay, how so?
Because the engine will ruthlessly terminate the loser. It forces developers to write their commands and internal scripts as pure functions, or at least ensure they are strictly idempotent.
Meaning they don't have side effects.
Exactly.
Yeah.
You cannot safely race a command that mutates state progressively. You only race retrieval operations, or operations that do all their computation in memory and only perform a single atomic write operation at the very end.
I see. So if it dies in memory, it doesn't matter.
Right. If a process is killed while computing in memory, the operating system reclaims that memory cleanly. There is no corrupted file on the disk. Moonshine's FRF paradigm essentially enforces functional programming principles at the shell orchestration layer.
You have to design your graph nodes to be side effect free if you intend to race them.
You have to, or you're going to have a bad time.
That makes a lot of sense. It forces better engineering practices. And to tie this all together, once you've forked these processes and race them, you have to move the data between them.
The folding part.
Right. Moonshine still uses the classic Unix pipe command, the vertical bar, but it replaces the underlying plumbing entirely. It utilizes high-performance Rust channels.
Which is a huge upgrade.
Massive, instead of using the host operating system's standard pipeline buffers, which can easily bottleneck when moving massive amounts of concurrent data, Moonshine moves the data through its own hyper-efficient memory channels.
This is a crucial architectural decision. Standard Unix pipes are essentially untyped byte streams managed by the kernel.
Right.
So when you are pushing gigabytes of telemetry data or massive JSON payloads between highly concurrent processes, the context switching overhead is huge. You are constantly crossing the user space to kernel space boundary to use those OS pipes, and it creates immense friction.
So how do the Rust channels solve this?
By utilizing MPSC, that's multi-producer, single consumer channels natively compiled in Rust. Moonshine keeps the data transfer entirely within user space memory, effectively bypassing the kernel's bottleneck altogether.
And this transition into Rust's memory management perfectly explains the engine's absolute obsession with speed. I mean, when you are managing a topological graph with thousands of nodes, forking pathways, racing concurrent pure functions, and folding massive data sets,
It has to be fast.
it has to be. The engine orchestrating all of this cannot introduce its own overhead. And Moonshine proves just how fast it is with a built-in diagnostic tool called the benchmark shootout.
It is incredibly rare to see a shell ship with its own highly opinionated benchmarking suite.
Right, like here's a tool to prove we're faster than you.
Exactly. It speaks to the developer's confidence in their architecture. They actively want you to test Moonshine's orchestration latency against whatever runtime you are currently using.
And the numbers they present in the source material are just staggering. They measure mean latency for two specific tasks. One is a built-in command, which is just asking the shell to execute a simple echo statement.
Just printing text to the screen.
Right. And the other is a math operation, specifically computing the Fibonacci sequence up to 20. And for both the basic echo and the math computation, Moonshine clocks a flat mean latency of 0.3 milliseconds.
0.3. The consistency between the simple I/O command and the computational task is the key takeaway there, I think. It shows that the engine's orchestration overhead is virtually non-existent, regardless of the workload type.
But then we look at the competition. They benchmark against Zhush, a staple for most developers, which takes 24.0 milliseconds for a basic command.
Considerably slower. Yeah. Then they test modern JavaScript runtimes. Bun comes in around 29 to 38 milliseconds. And Node completely falls apart.
Oh, Node really struggles here.
It takes 97.0 milliseconds for the built-in echo and a massive 207.0 milliseconds for the math operation.
207 milliseconds just to get started, basically.
The documentation explicitly credits Moonshine's sub-millisecond dominance to the fact that it is a highly optimized Rust binary, specifically compiled with the cargo build -- release flag.
Compiling an optimized release binary in Rust gives you zero-cost abstractions and incredibly fine-grained control over memory allocation.
So no bloated runtimes.
None. When you compare that to Node, the difference in architecture becomes glaringly obvious. When you ask Node to execute a command, it has to spin up the V8 JavaScript engine, allocate a massive memory heap, parse the JavaScript, run it through a just-in-time compiler.
That's a lot of steps. And it has to constantly pause execution to run garbage collection. All of that happens before the command even really begins to do its actual work. That is why you see a 200 millisecond latency.
Whereas
Rust does all of its memory management mathematically at compile time, meaning at runtime there is no garbage collector pausing the thread. It just executes raw, optimized machine code.
Okay, here's where it gets really interesting, but I have to play devil's advocate for a moment.
Please do.
Because if you look at 24 milliseconds for Zhush, you might think, wow, that's 80 times slower than Moonshine's 0.3 milliseconds.
Yeah.
But from a human perspective, a single physical blink of an eye takes about 100 to 400 milliseconds.
Yeah.
So even at its quote-unquote slow 24 millisecond pace, Zhush is returning a command faster than you can blink. If you're just a developer typing echo hello world into a terminal, you are completely incapable of perceiving the difference between 0.3 and 24 milliseconds.
You wouldn't notice it at all.
Right. So it feels like we are chasing microscopic performance gains that don't actually impact the user experience. Why does sub-millisecond latency even matter?
If the user experience was isolated to a human typing a single command, you would be absolutely correct.
Yeah.
But we have to connect this baseline performance back to the control flow graph. Moonshine is not designed for single human speed inputs.
It's designed to autonomously walk a complex topology.
Precisely. Imagine an automated continuous integration pipeline for the Gnosis monorepo. That CFG might contain 10,000 distinct operations.
10,000, wow.
If you are using a runtime like Node to orchestrate that graph, and every single time the engine transitions from one node to the next, it incurred a 200 millisecond penalty, you have a massive problem.
Oh, because it stacks.
It stacks heavily. In a sequential path of just 100 nodes, that is 20 solid seconds of pure engine overhead. That's 20 seconds where the computer's doing zero actual work. It's just figuring out how to run the next step.
It's a compounding effect. The latency isn't a one-time tax. It's a tax applied to every single branching path and node in the graph.
Exactly. When your baseline orchestration latency is locked at 0.3 milliseconds, the engine essentially disappears from the equation. The orchestration tax is mathematically negligible.
So the only time your build process spends is on the actual computation of the commands themselves.
Right. This is why sub-millisecond speed at the foundational layer scales exponentially when applied to massive topologies.
Okay, so we have a Rust-powered topological engine that is navigating thousands of concurrent branches at sub-millisecond speeds, racing processes, and aggressively terminating losers.
It's a beast.
It is a beast.
Huh.
But operating at that blistering speed creates a massive attack surface. If bad actors or rogue scripts get into that concurrent graph, they could execute catastrophic damage across a monorepo in fractions of a second.
Faster than any security system could catch it.
Exactly. Which inherently means that traditional security models, where the shell just blindly trusts whoever happens to be logged in, are completely inadequate for this kind of engine. And this brings us to Moonshine's most revolutionary shift:
Autonomic identity?
autonomic identity and cryptographic shells.
This is where Moonshine ceases to be just a fast shell and becomes a fundamentally new computing paradigm. Traditional shells operate on what we call ambient authority.
Ambient authority, right.
If your user account has read-write access to a directory, the shell assumes any script you run also has that access. The shell doesn't verify the script, it just passes the request to the OS, and the OS checks your user permissions.
Which means if I accidentally download a malicious dependency and I run it, my shell will happily let that dependency encrypt my entire hard drive because I have permission to write to my hard drive.
Exactly. The shell is just a dumb pipe in that scenario. But Moonshine rejects ambient authority entirely. It operates on a zero-trust model applied directly to the execution layer.
It requires a local identity.
Yes. It requires what it calls of a local identity to authorize anything. The setup initializes two specific cryptographic components. First, a local DID, which stands for Decentralized Identifier,
Okay.
and second, a UCAN foundation.
Let's break down exactly how this works, because if you are used to traditional environments, the idea of a shell requiring a decentralized identifier sounds pretty heavy.
It is a bit of a mental leap.
I have a good way to visualize this. Think about physical security. A traditional shell is like a standard office building. If you have the front door key, your user login, you can get inside.
Or once you're in, you're in.
Right. Once you are inside, you can wander into any unlocked office, open any filing cabinet, read any document. That's ambient authority. But Moonshine's UCAN architecture operates more like a highly advanced, programmable cryptographic keycard system.
That is a highly accurate analogy. UCAN stands for User-Controlled Authorization Networks. Instead of relying on a central server or an Active Directory to check permissions, UCANs encode the exact granular permissions directly into a cryptographically signed token.
So my local DID, my identity, is basically the root cryptographic key pair held securely on my machine.
Yes.
And when I want to run a complex topological graph, I don't just hit enter. I use the --UCAN flag to pass a specific capability token to the engine.
Precisely. And here is the critical mechanism. The Moonshine engine parses that token and verifies the cryptographic signature against your local DID's public key before it even considers spawning the process.
It does the math locally.
It does the math locally, yes. It checks the token to see if you have explicitly delegated the right to execute a specific command on a specific file path within a specific time window.
And if it doesn't match?
If the math doesn't mathematically prove you have that exact clearance, the engine refuses to create the process. It doesn't even ask the host operating system. The engine acts as an impenetrable cryptographic gateway.
It's verifying the math itself in line at 0.3 milliseconds.
Which goes back to the obsession with speed. It has to be fast to do this on every command.
That is incredible. And this zero-trust cryptographic model cascades down into how Moonshine handles configuration. I mean, standard environments use plain text.env files.
All the dreaded .env files.
Right. Developers just drop their AWS keys, their production database passwords, all into a hidden text file in the project root. The fundamental flaw there is that any process that achieves read access to that folder can instantly steal your entire infrastructure.
It is arguably the most common vector for supply chain attacks today.
Mm-hmm.
A malicious NPM package simply reads the local.env file and exfiltrates it to a remote server. Game over.
But Moonshine replaces this with .env.not files. The documentation describes these as identity-locked, signed, and encrypted environment variables.
If we connect this back to the local DID, the mechanism of the .env.not file is brilliant. When you create this file, Moonshine encrypts the sensitive variables using a cryptographic key derived from your specific DID.
So what does the file look like on the disk?
It's literal garbage data. It is pure cryptographic noise. If a malicious script reads the .env.not file, they get nothing they can use.
Because they don't have the key.
Exactly. The only time those variables are decrypted is dynamically in memory at the exact millisecond. The Moonshine engine mathematically verifies the UCAN token of the specific process requesting them.
So the secrets never exist in plain text on the hard drive, and they are only handed to processes that carry a cryptographically signed permission slip from the user.
It completely neutralizes the threat of ambient file scraping.
It completely insulates the execution environment from the host operating system's fragile file permissions. But Moonshine's cryptography doesn't just protect the inputs and the environment variables. And this leads to arguably the most fascinating, just mind-bending feature of the entire tool.
I know exactly what you're about to say.
If Moonshine doesn't trust the host operating system to store its secrets in .env files, it certainly isn't going to trust the host operating system to maintain its history.
You're referring to prismatic refraction.
Prismatic refraction and shadow mode. This is where Moonshine crosses the line from a defensive tool to an actively subversive piece of architecture.
It really is subversive.
When you run a command in a traditional shell, that command, along with all the arguments you pass to it, is usually recorded in plain text in the host operating system's system logs like syslog or the shell history files.
Which presents a massive security vulnerability.
Yeah.
If you pass a temporary authorization token or a database password directly as a command line argument,
Which people do all the time.
all the time, that highly sensitive data is permanently burned into the host's log files. If an attacker gains root access to the machine later, they can just read the logs and harvest every secret you've ever typed.
To prevent this, Moonshine utilizes prismatic refraction. The documentation explicitly states that every process name and argument is XR obfuscated in the diagnostic logs using your DID. Now, why XR obfuscation instead of full, heavy AES 256 encryption?
That comes directly back to our discussion about the 0.3 millisecond latency.
Ah,
If the Moonshine engine had to perform a full AES encryption handshake on every single argument of every single node in a massive concurrent graph, the performance overhead would destroy the sub-millisecond advantage.
it would be too slow.
Way too slow. XOR, exclusive OR, is a fundamental bitwise operation. It is computationally nearly free. By mathematically XORing the command string against a symmetrical key derived from your local DID, the engine scrambles the text instantaneously without incurring any meaningful CPU penalty.
And the result of this instantaneous scrambling creates an incredible dichotomy between what the computer thinks is happening and what is actually happening.
A literal shadow.
Yes. The text says that the host system logs only capture the shadow of the process. If you look at the activity monitor on your OS, you see a process ID, you see CPU spikes, you see memory being allocated. But if you try to read the command string,
It's just a scrambled mess of alphanumeric noise.
meanwhile, the Moonshine topological engine internally maintains the truth.
The tool even includes a specific invocation called shadow mode for highly sensitive commands. The documentation beautifully describes this as casting a quote-unquote thermodynamic trace while keeping the actual execution pristine.
Thermodynamic trace. That sounds like sci-fi.
It does, but practically it means it leaves a footprint of energy proof that compute resources were consumed at a specific time without ever revealing the what or the how to the underlying system.
Okay, I have to stop here and look at this from an IT perspective.
Yeah.
Because you are a system administrator, and honestly, this sounds like an absolute nightmare.
It is definitely a culture shock.
The entire point of system logs is to maintain an auditable trail of truth. If a server crashes or a workflow fails, the first thing you do is tail the logs to see exactly what command was run and what arguments were passed.
Right.
If the shell is actively lying to the operating system and filling the logs with mathematically scrambled shadows, how on earth do you debug a failing monorepo? Aren't you just blinding yourself?
It is a profound trade-off, and it requires a complete architectural shift in how an engineering team handles telemetry. You are absolutely right that standard sysadmin workflows rely on the host OS logs.
Right.
But Moonshine's philosophy asserts that in a modern cloud-native environment, the host operating system is fundamentally untrustworthy. You have to assume the host machine will eventually be compromised.
Assume breach.
Assume breach, exactly.
Okay.
If you assume the host will be breached, then the host logs are no longer a debugging tool. They are an attack vector. They're just a menu of credentials waiting to be stolen.
Wow, okay, I see.
By XOR obfuscating the logs, Moonshine neutralizes that attack vector. And to address your point about debugging, you aren't completely blind. You just can't use the legacy OS tools anymore.
So where do you go for the logs?
Because the Moonshine engine internally maintains the truth, authorized developers who hold the correct UCAN capabilities can query the engine directly for the unobfuscated execution history. You are shifting the source of truth from the operating system's generic logging daemon up into the secure, cryptographically verified enclave of the Moonshine engine itself.
The shell effectively becomes its own secure, auditable sandbox, which is conceptually brilliant. But practically, building a tool that leverages sub-millisecond Rust topologies, zero-trust UCAN cryptography, and prismatic refraction, it sounds like it would require a PhD just to install and configure.
Oh, absolutely.
Yeah.
Historically, that level of complexity is a nightmare to set up.
Usually, when a tool is this secure and this complex, the developer experience is utterly miserable.
That is the historical precedent, certainly. High security usually mandates high friction. But the architects of Moonshine clearly understood that if a tool is painful to use, developers will simply bypass it. They'll find workarounds.
They'll just use Zishmore.
Right. So they invested heavily in an ecosystem that aggressively abstracts all that complexity away from the user.
They built what they call the Magic Installer for macOS and Linux. And it is a masterclass in reducing friction. You run one script, and it autonomously handles 4 massive architectural setups.
It does everything for you.
It really does. First, it pulls down the Rust toolchain and builds the optimized release binary specifically for your machine's architecture. Second, it generates your local DID and initializes the entire UCAN cryptographic foundation behind the scenes.
Which is huge. Doing that manually takes forever.
Exactly. Third, it injects the Moonshine alias directly into your .zip or .bash RShip profile, so it immediately intercepts your commands. And finally, it runs Moonshine Doctor to cryptographically verify that the entire chain of trust is intact before you even type your first command.
It condenses what would normally be a multi-day cryptographic provisioning process into a single automated execution.
Magic.
It really feels like it. Though it is worth noting they do provide a manual route for CI/CD integration, which requires explicitly fetching the Rust toolchain via rust.hx before compilation.
So you can automate it.
Exactly. This ensures that automated pipelines can deterministically build the engine without relying on the interactive magic installer.
And once it's installed, the way you actually interact with this topological graph is through a highly specialized configuration syntax. The documentation highlights .not and .gnarly files. I love the naming convention, by the way.
.gnarly is fantastic.
It is, but these aren't just basic script files. The text defines them as GG family multilingual topologies.
The term multilingual topologies is where we really see the scope of Moonshine's orchestration capabilities.
Right. The documentation notes that these .gnarly files utilize a shared parser for metadata and feature embedded implementation blocks. Plus, they use an intricate import packaging system with specific source directives: context, mount, include, and exclude.
It's extremely robust.
Let's clarify how powerful this is. In a single .gnarly file, you could define a context that spins up a lightweight node runtime, mount a specific local directory holding your database schema, include an embedded block of pure Rust code to perform a hyperfast data transformation, and exclude all the testing directories to save memory.
All in one file. It acts as a unified declarative graph. You aren't writing bash scripts that awkwardly call Python scripts that awkwardly call Rust binaries, just crossing your fingers and hoping the exit codes align.
Which is how most of us do it.
Exactly. But here, you are defining a singular, unified topology. The Moonshine engine parses that .gnarly file, understands the dependencies between the embedded node blocks and the rest blocks, applies the UCAN security constraints to the specific mounted directories, and then unleashes the FRF paradigm forking, racing, and folding the execution across your CPU cores with 0.3 millisecond latency.
It is breathtaking orchestration. And to ensure the ecosystem remains pristine, the developers enforce a strict developer experience standard. If you want to contribute to the Moonshine codebase, you are required to run and pass the DX acceptance suite.
They take it very seriously.
They treat the developer experience as a first-class metric, on par with cryptographic security and raw performance.
Which brings us to the ultimate synthesis of this architecture. When you look at the holistic capabilities of Moonshine, it utilizes .gnarly files to manage multilingual execution context and isolated directory mounts.
Right.
It uses its internal doctor command to constantly verify a decentralized offline cryptographic chain of trust. It enforces functional programming through its topological FRF engine. And through prismatic refraction, it actively encrypts its actions to hide them from the host operating system's logging daemons.
Yeah.
This raises an incredibly important question about what we're actually looking at.
I have a feeling I know where you're going with this.
Is Moonshine actually a shell? We use that word because it accepts text input and launches processes. But functionally, architecturally, are we looking at the blueprints for an entirely new, lightweight operating system layer that is simply masquerading as a shell.
A parasitic operating system layer.
Exactly, a parasitic OS. It possesses all the autonomy, security verification, and complex resource orchestration of a modern OS kernel. But instead of running on bare metal, it runs parasitically on top of Unix, stripping away the host's authority and replacing it with its own mathematical truth.
That is a brilliant way to conceptualize it. It perfectly captures the journey we've taken today. We started by looking at a tool designed to solve the annoying waiting game of the traditional command line, and we peeled back the layers to uncover a sub-millisecond Rust-powered engine that rewrites the laws of execution.
An engine that maps commands into graphs, races them concurrently, and actively assassinates the losers to conserve compute cycles.
It completely redefines the boundaries and responsibilities of the command line interface, shifting it from a dumb messenger to a hyper-intelligent, zero-trust gatekeeper.
It really does. It demands cryptographic proof of identity through UCAN tokens before it acts.
And it utilizes prismatic refraction to cast untraceable XOR-obfuscated shadows into the system logs, deliberately blinding the host operating system to protect the integrity of its data. And, nothing captures the sheer audacity and elegance of this architecture more perfectly than the poetic quote placed at the very end of the README documentation.
Oh, yes.
It simply states, "Moonshine is the ghost in the shell if the shell was a prism."
It is a rare piece of technical documentation that manages to be both hyper-precise in its engineering and deeply philosophical in its framing.
It really is.
The quote perfectly distills the essence of the engine. Ethereal, autonomic, mathematically untouchable, yet refracting your commands to split the internal truth from the external shadow.
It's incredible. And it leaves you with a lingering, almost unsettling question to ponder long after you log off today. We have just explored an architecture that is evolving to a point where it fundamentally assumes the host environment is compromised.
It doesn't trust the house it lives in.
Right. It actively hides its truth from the underlying system logs to protect itself. If the tools we build are becoming so advanced that they no longer trust the operating systems they run on, and if the shell is becoming an independent cryptographic ghost who is really in control of the machine,